Yeah, good morning to one and all. Today we'll start the session.
Good morning, ma'am.
Good morning to one and all. Okay. Yeah. Now, in today's class, I'll be going to explain you in brief about what we have discussed in yesterday's class. In the more and the second, I mean, it is as it is a combined class. Some for some students, the ABCD parameters derivative part is not over for pi model, and for B section, I think so, or A section or B section. I didn't remember, but I'll tell in brief and I'll go for the problems then. Okay, all of you listen to me carefully. It's very, very important as a okay. Right. Now, see here in the nominal pi method, we have dealt with the nominal T method in medium transmission lines. This is the nominal pi method representation. See, this representation is a pi model. We have discussed already that in this method, capacitance of each conductor, that is the line to neutral. This is the line, this is the neutral line. And the line to capacitance of each conductor, that is line to neutral, is divided into two halves. This is one half and this one is the other half. We have it is divided. One half being lumped at the receiving and sending end side. This is the sending end side. This is lumped at the sending end side. This half of the capacitance is lumped at the sending end side. We can say this another half of the capacitance is lumped at the receiving end side. Receiving end side. Okay. It is that the sending end has no effect on this, and you have to note one thing that this capacitance IC2 has no effect on this drop. Why? Because it is passing through this. It is an additive to that of this line current. It is an addition. It is an additive to that IC2 plus IL would be there. IC2 plus IL gives you the IS. That means there won't be any drop in this particular IC2. IC2 capacitor current. Okay. Now the charging current must be added. This charging current must be added to that of the line current in order to obtain the sending end current, as we all know. This is the sending end current. This is the entering current. According to the KCL, sum of the currents entering is equals to sum of the current leaving. This is the entering current. IS is the entering current and the leaving current is IC2 and as well as the IL. So this charging current added to the of the line current is equal to the sending end current, we can say. Now IR is the load current, as we all know. Resistance R is the resistance and Z is XL is the inductive reactance per phase and C is the capacitance per phase. And cos phi r, if at all we know what is the phi r, this is the angle between the sending end, receiving end voltage and receiving end current. This is the receiving end current and this is the receiving end voltage. Phi r is the angle between the receiving end current and voltage. What is phi s? It is the angle between the sending end current to that of the sending end voltage. If you apply cos on both the sides, it will be giving you the sending end power factor. It will give this is the this is the sending end power factor. This is the receiving side power factor we are having. Cos phi r is the receiving side power factor and the cos phi s is the sending end side power factor we'll be getting. Okay. Now let us have a phasor diagram. This is the phasor diagram what we know, and this phasor diagram I've already explained in the class, but I'll tell you in brief. This is the phasor diagram we are having. Okay. Now taken VR as the reference. We are taken VR as the reference. We have taken VR as the reference. IR lags VR by an angle of phi r. IR lags VR by an angle of phi r over here. See here, we'll be having a leading current IC1. IC1 leads V1. This is the IC1 current. See here, towards that of the receiving end side. VR is taken as the reference. IR lags VR. First term, this one. Each and every of the term we have to represent in this phasor diagram. Let me go from this side. First VR. VR is taken as the reference. Now I'll go for the IR. IR lags VR by an angle of phi r. This IR lags VR by an angle of phi r. We are having IR over here. Now this is the thing. IC1 is the charging current. What is this current called? This is the charging current which is made to flow through this capacitors. This IC1 leads VR. The IC1, the capacitor current obviously leads via voltage by an angle phi. This is the capacitor current. See, this is the capacitor current IC1, which is in the receiving end side, which leads VR. VR means actually it must be there here. But because of the convenience, we have drawn over here. See here, this is the IC1 is the capacitor current which leads VR. If you extend this line, this would make an angle of 90 degrees. If it is a pure capacitor, it makes an angle of 90 degrees, which is the leading angle. See here, I have made this. This is the leading angle makes with that with respect to VR. IC1 leads VR by an angle of 90 degrees, we can say. IC1 leads VR by an angle of 90 degrees, we can say. So, what is the resultant of IR and IC1? IL. See here in the figure, this is the resultant for both these two. This is the entering current to this point, and the leaving current is would be IC1 and IR. Okay, so some of the current, this is the resultant of it. That is why we have kept, this is the resultant of both this IR and IC1. This part is over. Now coming to the drops. Now coming to the drops whatever we are having. See, this is the resistive drop what we are having. This is R into IL. R into IL. IL is the current made to flow through this line. Okay. This XL into IL current is made to flow through this line. See here, there is a resistive drop. This drop should be in parallel with that of this line. This is the resistive drop. See here, these two are parallel to each other. The line current is IL. Because of the line current is made to flow through this resistance, this is the resistive drop which is in phase with that of this. So IL into R. And the inductor drop which is makes an angle 90 degrees to that of this, and this is like this, and the resultant would be, see here, this would be the resultant. We can say that it is a Z. If you want to write like this, here like this, it is not a problem. You can write it as IL into Z. You can write it as what you can write, IL into Z. You can write it as IL into Z. But here this part is over. Up to here it is over. Up to here it is over. Now coming to this part. What is the sending end? Sending end, this one, sending end voltage. Now see here, this is the sending end voltage. How to find the sending end voltage? Sending end voltage Vs is equals to Vr plus this drop. If you consider this entire loop, if you apply KCL, then you will be getting the Vs is equals to Vr plus IL into Z. IL into Z you can write it as a. So this is the resultant of this Vr and this drops. This is the resultant of this drop. See here. See, Vs is the resultant of this VR receiving end reference voltage plus this IL into Z. Okay, we can say, or else you can combine like this. These are the VR plus IL into R and IL into XL, which is nothing but IL into Z. It is a resultant of VR plus IL into Z. Vs is equals to. Once after finding the value of Vs, the current, the sending end current Is is the vector sum of. See here, the sending end current is the. Now, what is it? This is the sending end current we are having. The sending end current is the vector sum of IC2 and IL. IC2 and IL. What is IC2? The charging current. What is this called? This IC2 is called as the charging current, which leads by 90 degrees to Vs. Which leads Vs by 90 degrees. See, we have to draw like this. This is the leading current. Actually, it is leading to Vs. It would be like this. But for the convenience, I have written over here, this is the leading current which makes an angle 90 degrees with that of Vs. This is Vs, right? This is Vr and this is Vs. See, this is the leading current IC2. If Is is the resultant of both IL and IC2 from the figure. See, Is is equals to IL plus IC2. So, Is is equals to IL plus IC2 we have to add. This is the resultant of it. Now, the angle between the sending end voltage Is and Vs is nothing but angle between Is and Vs is nothing but the phi s. We will be having as phi s, which is nothing but cos phi s, we can say. Cos phi s, if you put, this is the power factor at the sending end side we will be getting. If you know this angle, you will be knowing the power factor angle. What is that? Cosine of the angle between the voltage and current. How can you define power factor? Cosine of the angle between the voltage and the current at the sending end side. At the sending end side. So, Vs and Is. The angle between Vs and Is is nothing but cos phi s. The angle between Vr and Ir is nothing but the phi r. That is the sending end side power factor. This is the receiving end side power factor, and this is the sending end side power factor. This is how you need to explain the phasor diagram. Very, very important and easy. Okay, let us do how we will calculate the, if we take Vr as taken as the reference. See here, Vr is taken as reference. This we have dealt in the last class, but for most of those who are absent for the last class, as it is a combined class, I am repeating once again so that it will you can understand better and you can do well in the problems, numericals we can do better. Okay, VR is equals to, this is taken as the reference. See here, this is taken as a reference. Now, what we can say that the IR is nothing but the IR current is nothing but IR. This is the IR current. So, we can write it as IR at an angle of IR. Just in the case of short transmission line and medium transmission line T network model, we have taken this. Okay, this IR lags VR by an angle of IR. So, that of minus IR, we can write it as this is of IR cos phi r minus j sin phi r, we can write minus j sin phi r, we can write. Okay, this is all. Okay, we'll be getting this. This is the vector we are having. IR bar is equals to magnitude and its angles. Okay, now the charging current. Now, how can we draw this charging current? See this figure. This is the charging current I am drawing. Charging current. Charging current at the load side is nothing but what is the load side charging current? This IC1. This IC1. How could you get this IC1? IC1 is equals to, we know the formula that Y into V, actually Y into V is the formula. I is equals to YV is the formula as that from the Ohm's law. V is equals to ZI. Z is the inverse of Y. So Y into VR we can write. What is this Y we are having? J into 2 pi F. J into 2 pi f we are having. See here, how you got this I have explained you in the last class. C by 2 we can say, this is of C by 2 or Y by 2, whatever it may be. This we can write it as C by 2. Okay, capacitance by 2. The capacitance is made half. Okay, okay, C by 2 into VR bar, we can write it as VR. Okay, now how you got this? As Z is equals to 1 by omega C, right? XC is equals to, what is XC? XC is equals to 1 by omega C, we know. 1 by omega C. If you, this is nothing but the Z, we can say. Z, we can say. If you want to write in Y, what will happen? J into omega C will be getting. But here we will be having by 2 we are having. So we are doing by 2 over here. That's what I have written. That's what I have written. Omega is nothing but 2 pi f. What is it? Omega j into 2 pi f. We have to write 2 pi df c by 2. C by 2. 2 gets cancelled. Okay, you will be remaining with j into pi f. This will come in the case of simplification. Don't worry. If you don't cancel 2 by 2 also, it doesn't make any problem. Okay. Now this is the IC1 is equals to Y into VR. This is the thing. Now what is the line current? Line current is equals to line current. Line current is equals to IL. IL is equals to, what is it called? See here, IL bar is equals to IR plus IC1. IR plus IC1. See, if you see the figure, you will be able to understand. See, IL is equals to, the sending end current is equals to both these currents. Okay, at this particular node. This particular node. IL is equals to IR plus IC1 it is. IC1. Okay, IC1 it is. Okay, now this can be resolved like this. And here this can also be written as this IL. How can you write this IR? IR mod cos phi r. We can also write like this, cos phi r minus j sin phi r minus j sin phi r. Okay, this is the thing for IR. For IR bar it is. For IR bar, I mean separating the magnitude and angle plus IC1 I am having. What is IC1 I got? This is the thing IC1 I am having. So I am putting this IC1 J into 2 pi F 2 pi F C by 2 C by 2 into VR I am having. Into VR I am having. What is there in my hands? I am having IL I am having in my hands. I know IC1. I know IC1. What I find out in this? I know IR. IR also I know. I know VR is equals to the reference I have taken. All this I have calculated. Now what I should calculate it? The sending end voltage I should calculate it. What is that sending end voltage? Vs is equals to VR plus IL into Z, the line current into the impedance Z it is. Okay. Now, what is this VR? What is VR we are having? See here, this VR plus J0 we have considered plus IL into R plus J into XL. R plus J into XL I can write. I can write like this. Okay. Now charging current IC2 at the sending end I want to find. This is the charging current at sending end at the sending end I want to write. This is IC2. See here the sending end charging current is sending end I want. What is it? That is equals to IC2 bar is equals to J into omega C by 2 into Vs bar. These on simplification you will be getting what? If at all you substitute J is equals to 2 pi F, 2 gets cancelled, you will be remaining with the thing is J into pi FC, J into pi F, this is F, C, pi FC into Vs bar. Now, sending end current. Now we need to find the sending end current. What is sending end current? Sending end current is nothing but, see, this is the sending end current. Is is equals to, how could I write? Is is equals to J omega IL plus IC2. IL plus, if you write simultaneously with me and you can understand it, it is very easy. All of you see here, the sending end current is equals to the IC2 plus this one. Okay, this is the IL current is made to flow. This is the IL current, line current, which is made to flow. IS is equals to IL plus IC2. Okay, now if you want to find the receiving end side, if no load current, no load voltage I want to find, that is IR dash I want to find at no load, that is at no load. At no load I want to find. See, I will go for the next slide so that you can understand. See here, this is the receiving end side. At no load, no load voltage I want to find. Why? Because at no load voltage minus full load voltage minus VR by VR into 100, if at all we do, into 100 we do, this is nothing but the voltage regulation will be happening. No load voltage minus full load by full load, receiving end side full load by full load is into 100. We can write the voltage regulation like that also. Voltage regulation can be defined in two ways. Sending end voltage minus, voltage regulation it is, sorry, it is voltage regulation. It is not efficiency. It is of voltage regulation percentage voltage regulation, we can say voltage regulation. Since it is a percentage, we have multiplied it with 100. How can you define the voltage regulation? Either you can, if you know the data of sending end voltage and receiving end voltage, you can write it as voltage, sending end voltage minus receiving end voltage, VR minus Vs minus VR by VR into 100 is also one formula. VR by VR into 100. This is one formula. And at no load conditions, if you know the no load voltage minus the receiving end side full load by full load into 100 is also one of the formula. Then how to find the VR dash value? How to find the VR dash value we will be going to see now. VR dash actually small one it will be, whatever it may be, small or big, whatever it may be. See here at no load. At no load, we don't have this current. That this is current would be becomes 0. This current becomes 0. That means the whole part, this part won't be there, and the equivalent circuit by under no load would be like this. How could be the equivalent circuit diagram? See, I'll draw here. This is the voltage, whatever the voltage at no load is, since IR is equals to 0, this would becomes like this. Okay. The only capacitor will be placed over here. This is the capacitor. We'll be having, what is the capacitor value? J omega C by 2 would be the value of this, and this would be the R, and this would be the JXL. J into XL will be having C. Whatever the current which is made to flow is nothing but the line current only will flow. IR would be 0. IR would be 0. Why? Because see, this is the line current or the sending end current. Both are same. See here, this is the line current would be flowing through this. This is the line current made to flow. See, this current is made to flow. This all this resistance and inductance would be, this would be the equivalent circuit diagram. Equivalent circuit diagram at no load. At no load. At no load. This equivalent circuit diagram has been reduced to like this. Why? Because if there is no current passes through the load, if there is no load, we have to remove this part, and this part won't be there, and the voltage across this is nothing but the y by 2, that is nothing but j into omega c by 2 will be having. This is the no load voltage, we can say. No load voltage VR dash, we can say. See, this is nothing but this. How could you write the equation for no load voltage? This VR dash is equals to IS into the sending end current. The sending end current is nothing but this one. Whatever the current is made to flow through this line, this is the sending end current into V is equals to IR, no, minus J by omega C by 2 with this. Okay. Now, this can be further simplified as IS can be written as VS by the total whatever we are having the reactance, that is R plus JXL, JXL plus minus J by this inductive capacitive reactance, so minus J omega C by 2 we are having the total reactance into this part. Into this part we can say J by omega C by 2. Okay. See here, if it is this is the no load voltage. Once after we know the no load voltage, we know the receiving end voltage VR. VR at an angle. VR, what we have taken? VR is equals to VR is equals to VR plus J0 we have taken. VR plus J0 reference we have taken at full load, right? This is the reference voltage we have taken. This is the full load receiving end voltage we have to know. Okay, once this is nothing but the at no load, this would be the term we are getting. After equivalent circuit diagram of at no load, this would be the diagram, and no load voltage is this. No load minus full load is this one. By full load, if you do, it will be into 100. If you do, then it will be percentage regulation you can find, and you can find once after knowing this, you can find the efficiency. We can find that efficiency is equals to power by output, power by output plus losses. What are those losses? D into IL square R losses here. IL square R losses. Whereas in case of nominal T method, what are the losses? Losses would be 3 into is square r by 2 plus 3 into ir square r by 2 in case of nominal pi method. But here in this case, this would be 3 into il square r only. Why? Because the line which is over here r and x is not divided. We have only r and xl. But in the case of the nominal t method, r is divided by 2 and xl is divided by 2. Here the capacitance is divided on both the sides, lumped on both the sides at the receiving end side as well as on the sending end side. This is how you need to find the efficiency calculations and voltage regulation for whatever may be the, this is the nominal pi method representation. If suppose this is how you have to represent for nominal t also. For nominal t methods, it won't be c by 2, it will be c only. Now then what you will be getting? Vs into j omega c by r plus jxl minus j by omega c. By 2 won't be there in case of nominal t method, whereas in nominal pi method we'll be having by 2. Okay, why? Because the capacitance is divided into two halves. Okay, this is how you need to find the percentage regulation and efficiency for a particular medium transmission line. Now we'll go for the generalized circuit constants in nominal pi method. For generalized constants for nominal pi method representation, first of all, this is the diagram as usual we have seen the many times. This now from this I will be writing R plus Z is equals to R plus J into XL, R plus J into XL. Now this is nothing but the series impedance per phase. What is this called? This total Z is nothing but the series impedance per phase, and y is equals to j into omega c we can write. Y is equals to j into omega c we can write. Remember these two are vectors. This is the y is nothing but the shunt admittance. Shunt admittance we can say. Shunt admittance it is. Admittance it is. Shunt admittance it is. And now, as we all know that IS is equals to IL plus R, we have derived in the last slides that in the medium pi method representation, IS is equals to, from the figure you can write IS is equals to IL plus IC2, IL plus IC2. All of you please note it down simultaneously so that you can understand better. IL plus IC2. This would be the equation 1. This is the equation 1. What is IS? What is IC2 again? IC2 is nothing but Vs into I is equals to YV. Vs into Y by 2 here. Here because of Y by 2 we are having C is divided by 2. So we can write this IC2 like this. IL bar plus Vs into Y by 2. Why? Because I is equals to YV formula we know. I is equals to YV many times I told. I is equals to YV. From Ohm's law only Y into V. So Y V is nothing but this one. V is nothing but the sending end voltage. This is V is nothing but the sending end voltage. This is Y we are having Y by 2. Why Y by 2? Because the capacitance is made half on both the sides. That value we have considered is Y by 2. Okay, admittance by 2, that is why we have written as Y by 2. So IL plus Vs into Y by 2, can I write like this? Let us suppose this is equation A. This is equation A, and I will substitute the values of IL plus IL is equals to, see here, I am having IL is equals to, these are all from the figure itself. IL is equals to IR from the equivalent circuit diagram only we have to resolve all these formulas. IR plus IC1. Okay, this is the current. IL current at this particular node. Entering current is equals to the leaving currents. So this is the one. Now how can I write this? IR plus IC1. How can I write this? This I can write it as, see, if I write IC2, this is nothing but Vs into Y by 2. If I write IC1, it is nothing but, it is there in the receiving end side. We can write it as VR into Y by 2. VR into Y by 2, which is nothing but IR, IR plus VR into Y by 2. Let us suppose this is equation 2. What is equation 1 we are having? Equation 1 is equals to IS is equals to IL plus IS2. See here IS is equals to IL plus, this is IL, no? IL plus IC2 is the first equation I have taken. IL is equals to IR plus IC1 is the second equation I have taken. Now what I know, Vs is equals to, I know this from the equivalent circuit diagram. Vs is equals to VR plus IL into Z, IL into Z. See here IL into Z. This is nothing but the equation 3. We can say this is nothing but the equation 3. Sending end voltage is nothing but the equation 3. Can I substitute this value of VR? See, all are vectors over here. You have to put bar. All are vectors. So VR plus VR plus IL is how much? This one you have to put like this. Substitute this equation 2 in equation 3. Substitute equation 2 in equation 3. We will be getting VR into Y by 2. Substitute equation 2 in equation 3. So that you will be getting this, instead of IL, you can place what? Instead of IL, you can place this value into Z. What is Z you are having? See, this is the one where I keep like this. This is the one. This is nothing but the Z, right? Z. Okay. Now, how can you resolve this equation? Vs is equals to VR. If I simplify this equation further, see all of you, I simplify further this equation, VR plus IR into Z, multiply. I multiply each and every of the term, IR into Z plus VR into Y by 2 into Z I am having, Y by 2 into Z. I just multiplied this Z with these two terms. Now I got this one. Now can I take VR as common in these two? VR as common in these two, this equation and this equation. Can I take VR as common? Now I will be getting 1 plus YZ by 2 I am getting. YZ by 2 I am getting. Sorry, this is YZ by 2. If I get YZ by 2, what it happens? See what I will remain with? I will be remaining with YZ by 2 I am having. See, these two terms I have taken plus what else I am remaining with? plus IR into plus IR into Z, IR into Z I am having from. If I compare this equation with this equation, see here Vs is equals to, we know from the two-port network, if you take any four-terminal network, we have sending end voltage and the receiving end, sending end current is written in two equations, A into VR plus B into IR. If you compare this equation, general equation, this equation, let us suppose, whatever the may be the equation over here, this equation, if you compare with this, let us suppose it is a equation P, let us suppose. If I compare this equation P with this equation, what I will be getting? A is nothing but this part and B is nothing but this part. Okay, why? Because IR into Z. So B instead of B I am having what? See, I will be getting A and B from these equations. A is equals to 1 plus YZ by 2 I am getting 1 plus YZ by 2 YZ by 2 I am having, and B is equals to, what is the equation I have got? B is equals to Z I am having. Same way in the case of this nominal T method, what we have calculated now, see ABCD parameters from this circuit diagram. Here from this circuit diagram, equivalent circuit diagram, we are calculating the AB parameters. Okay, we are this is nothing but Vs. Okay, Vs equation only. No, this equation equal to Vs is equals to Vr into 1 plus Yz by 2 plus Ir into Z. Let us suppose this is equation A. Compare equation A with P, we can say this is equation A. Let us suppose this equation is compared with this P equation. Now you will be getting A and B like this. A and B like this. Now let us go for the another one, which is nothing but the CD parameters. In order to find the CD parameters, we will go for the current equation. Let us see here. See what is IS? IS is equals to, IS is equals to, what is it? IL plus IL plus Vs into Y by 2, that we have derived in the last slide. See here Is is equals to IC2 plus IL, right? This IC2 I have written into Vs into Y by 2. That is how I have written. Okay, putting the values of 2 in equation A. See, this is equation A. Let us suppose this is the equation A we have derived. At the top we have derived this also. See, this is the one. Now 2, what is the 2 equation? IL is equals to, now I have to substitute in place of IL. What is IL? I have to substitute. IL is equals to, what is IL? IL is equals to IR plus IC1. Now I have to substitute this one. IR plus VR into Y by 2. VR into Y by 2 plus Vs into Y by 2 I am having. Okay, let us suppose this is the equation B. Let us suppose this is the equation B. Okay, now putting the values of Vs from equation A to B. See what is the equation A we are having? Vs we are having this equation. See here Vs we are having this equation. This equation is nothing but capital A we have. So put this equation in this Vs term. Now it is simplified as, it is the one we will be getting like this. Is by putting the value of A. Put equation A in B, in B equation, if you put, then what is equation A we are having? All of you look here. This Vs is equals to Vr 1 plus Yz by 2 plus IRz. This is the equation way. Put it in this Is. Is is equals to IR. This as usual common. We'll be having the first term common. IR plus VR into y by 2 plus, we have to substitute Vs. Vs is what? Y by 2, if I take common, y by 2 is taken, this one, this is out. So, I will be having VR as, see here, Vs as VR into 1 plus yz by 2, yz by 2 plus IR into Z plus IR into Z I'm having. Okay, this is just simplification, just putting the values of one values to the other values in order to get the ABCD parameters. Now simplify it. This is all of you try to note the main equations so that will be, if you go through that, it is very easy for you to understand. Y by 2 plus VR into y by 2 is this one. VR into y by 2 into 1. VR into y by 2 we are having plus see here it will be VR into this equation if you multiply VR into yz by 2 into y by 2 we are having. So we are having y square by 4 this is y square by 4 into z y square by 4 into z plus y by 2 into this y by 2 is multiplied with this term so that y by 2 into IR into z IR into z. This is the equation what you have obtained from IS. Now this equation is compared with this equation. Now let us suppose this is the equation. See, taking the common terms, VR into y by 2, VR into y by 2, what it becomes? It becomes VRY. Okay, VRY it becomes. Is it not, students? Two halves are added together, it becomes full, right? VR plus, here two halves are added. Okay, then it what it becomes? VR into y. Is it not? Yeah, this is the two equations you have got. Now IR into, see here, if I take IR as common, this is the one I am having, 1 plus, wherever I am having IR, here I am having. See here, YZ by 2 I am having, YZ by 2, YZ by 2. This is the term IR one term and this is one term IR one term I am having. If you add these two, IR is common I have taken, IR is equals to 1 plus YZ by 2. What else we are having? VR into Y I have taken as common. See here, this becomes VR into Y. This 2 becomes, 2 halves becomes what? 1 full. VR into Y by 2 plus VR into Y by 2 becomes VRY. So I will be taking common VRY from these two terms. This is this term and this term. See here, this term is there and these two terms are there. I have taken VR into Y as common so that I will be getting 1 plus YZ YZ by 4. YZ by 4. Now, if I compare this equation, IS is equals to C into IR, C into VR, sorry, C into VR. Compare this equation with this equation. What is the general equation we'll be having? See, IS is equals to C into VR, C into VR plus D into IR will be having. D into IR. This equation is compared with this. Let us equation, it is P2. P2. This P2 equation is compared with this equation C. What you will be getting? P2 is compared with C. See here, VR into C into VR means what is C? C is equals to, compare this equation of C and P2. P2 is here. See, all of you look at me carefully. This is P2 equation. This equation is compared with this equation. You will be getting C into VR. See here we are having C is nothing but what? Y into 1 plus 1 plus yz by 4. Yz by 4 you are having. Okay. Now, what is D you are having? D should be equal to A. D should be equal to A, which is nothing but 1 plus yz by 2. See here, if you get the values D value and A value is same, then only your derivation part is correct. Otherwise, it is clear that you might be went wrong somewhere. You have went wrong somewhere. Okay. See here, this is D is equals to 1 plus yz by 2 you are having. What is A we are having? 1 plus yz by 2. So, we can say that A is equals to D. A is equals to D we can say. We can say that A is equals to D 1 plus yz by 2. I'll write here all the four parameters. All of you see here. Let us check whether AD minus BC is equals to 1 or not. Okay. We will be having now. This is the thing we are having BS into IF. Now how can we put this in equation form? See, this is the ABCD parameters we are having. We will be putting as VS into IS. See here. This is VS, this is IS we are having, IS we are having in matrix form if you want to put that is equals to, what is A we have got? A is equals to 1 plus YZ by 4, YZ by 2, 1 plus YZ by 2 we have got. In case of T network what you have got? 1 plus YZ by 2 only you have got in T network also. All of you look at that one. If you have derived in your notebook, then you can observe that. What is B we are having? What is B we are having? See here, B we are having as Z. What is B? Z we know. After comparing, what is C we are having? Y into 1 plus YZ by 4. This is YZ by 4. Okay. Now, what is D we have got? 1 plus yz by 2. 1 plus yz by 2. Okay. Now you have got this. This is equal to VR IR. What is it? This is VR and IR in matrix form. In matrix form. Okay. This is the thing. This is how you have got it. What is this part? This is nothing but A. Okay. This is B and this is C and this is D. See here you can observe that A is equals to D. A is equals to D. Okay. So our derivative part is correct. We can conclude. We can see another one, it is that AD minus BC should be minus equal to 1. AD minus BC should be equal to 1. We have to check it for that. Okay. Now AD is what? See here, this is A, this is D. How can we say that? 1 plus yz by 2, 1 plus yz by 2 whole square we can say AD. Same values A and D, so square minus B is Z, C is nothing but Y into 1 plus YZ by 4. YZ by 4. Okay. If you simplify further, this you will be getting as, see here, this if you simplify further, A plus B whole square, it is in that form. So A square plus B square plus 2AB, A square plus B square is nothing but Y square Z square by 4, Y square Z square by 4 plus 2AB. 2 into AB is nothing but YZ by 2, YZ by 2 gets cancels. Okay. Minus YZ we are having. Okay. Minus YZ plus, so minus into plus minus, what we are having? Y square, again Z square by 4 we are having. So minus this one and plus this one cancels, plus yz and minus yz get cancelled. You will be remaining with 1. You will be remaining with 1. So we have proved that this AD minus BC is also equal to 1. So it is hence proved that our derivative part is correct. If at all, if it is not equal to 1, you might be went wrong somewhere. You might be went wrong somewhere. Now see here the difference between the see ABCD parameters for T network. Let us suppose for T network, what would be the ABCD parameters? Can any one of you tell what is the ABCD parameters for T network? We have derived in the last classes.
A equal to 1 plus yz by 2, ma'am.
Yz by 2, very good.
B
B is equal,
equal to z into 1 plus yz by 4.
very good. Z into 1 plus
Yz
Yz,
by 4.
Yz by 4, very good.
C
Now,
equal to y.
yeah, C is equals to
Y.
Y, D is equals to
1
1,
plus yz by 2.
very good, 1 plus Yz by 2. Okay, these are the ABCD parameters for T network what we have obtained. Now coming to the pi network. What is the pi network representation? Just now we have done. The pi network is nothing but this one. We have done just now. See, I will be showing you what is pi network A. 1 plus 1 plus yz by 2. Yz by 2. This
B
is
equal to z.
B is equals to Z, very good. C is equals to Y
Y
in
into 1 plus yz by 4.
YZ by 4. YZ by 4. Okay. Next one, what is it? 1 plus
Yz by 2.
YZ by 2. Okay. See here in each and every of the case, you'll be having A and D are equal. If at all we do AD minus BC, you'll be getting equal to 1. This is how we can check whether our derivative part is correct or not. If at all any problem also, if you check that one A is equals to D you have got and AD minus BC is equals to 1, then your answer is correct. Then it satisfies VS IS. This is written as VS IS is equals to VS IS is equals to matrix form if you want to write. Matrix form if you want to write. C that is equals to VR into IR we can. VR into IR. That is the case in the case of both nominal T method and nominal pi method. With this we have completed the derivative parts. Okay. Now in tomorrow's class, I mean in the next class, we'll do problems. Time of today. I thought I'll tell you the problem also today, numerical, but time is not sufficient. It's already 11:26 or something else like that. We have to wind up the class. So here is this. If you see this here like this, see all of you, if you multiply, this is the matrix, no? If you multiply these words, see 1 plus yz by 2 into VR plus z into IR gives you VS only. IS is equals to what? This into this. If you check like that, you will be getting the values. See, if at all you want to cross check, if you remember this ABCD parameters only, if you don't know how to write these equations, if suppose some of the people they might forget how to write the equations, they may get little bit confusion. Then if you remember this ABCD constants from these equations, you can write what is VS and what is IS. Okay, this is in terms of if at all in some of the problems they'll be giving you the admittance and impedance values. They'll ask you to find the sending end voltage and sending end current. In such cases, if you know the values of Y and Z which is given in the data, you can find the sending end current, I mean sending end current and sending end voltage. Once after the sending end current and sending end voltage is known, you can find easily the power factor for that. What is the power factor? Is the cosine angle between the voltage and current. If at all you multiply these two equations, you will be getting one equation and you know the angle of it. Then this angle, voltage angle minus this current angle, if at all you do, that is nothing but cos of that angle gives you the power factor at the sending end side. Power factor at the sending end side. Likewise, you have to simplify the equations very easily once if you know the values of ABCD parameters. In some of the numericals, they'll be given you the YZ values only. They'll be asking you to find the Vs and Is, Vr, whatever it may be, cos pi s, whatever it may be. In such cases, you have to remember this ABCD parameter constants so that you will be getting the equations very well. Okay, that is how you have to solve the problems in some of the cases. Understood, students? This is regarding the nominal T and nominal pi method. With this, we have completed the theoretical part. And for tomorrow's session, the next session, we'll be going to do the numericals on this. Nominal pi method, model of representation.